Welcome to the site, everyone. Grab your hard hats because I am your chief architect for today's explainer, and we are staring down the barrel of a major high-stakes construction project. We're looking at the Cambridge AS and A-Level Mathematics 9709 Integration Trapezium rule. Now, the goal here is simple but absolutely rigorous. We are learning exactly how to lay down an unshakable mathematical foundation to accurately approximate the area under a curve. You know, so many students walk into the exam hall and treat their paper like a pile of loose, unconnected formulas, and what happens? Their grade completely collapses the moment the examiners apply even a little bit of pressure. But not you. Not after today. Today, we're going to teach you how to erect heavy, load-bearing analytical arguments. We'll show you how to properly substitute your coordinates and evaluate your curve structure so thoroughly that your answer will survive the most brutal examiner stress testing. Let's get to work. Okay, so let's dive right into the numbers. The trapezium rule accounts for a massive 15% of your total paper 2 marks. Think about that for a second. 15%. That makes it a critical load-bearing pillar for your final grade. It's literally the difference between an A and a B, or a B and a C. You simply cannot construct a top-tier A-level grade without completely mastering this specific numerical integration technique. That 15% is the difference between a mathematical structure that stands tall against the skyline and one that entirely fails the final site inspection. And here's the thing. We aren't just looking for the final number or area. Anyone can punch numbers into a calculator. We are building an entire framework of mathematical logic. We have to demonstrate the full, step-by-step method of calculating your interval widths and precisely mapping the appropriate y values. To secure those marks, we are going to follow this strict industrial blueprint today. We'll start in the blueprint room, move on to reading the system blueprint, listen in on the ironwork peer debate, conduct a mid-build inspection, and wrap up with the viewer rebar stress test. Let's kick things off with Section 1, the blueprint room. Before we pour a single drop of concrete or write out a single equation, we need to analyze 2 very common contractor profiles that we see all the time. This brilliantly illustrates our baseline problem. First, we have builder Alex. Alex walks into the exam hall and just starts frantically stacking raw facts. They've memorized the formula, sure, but they don't actually understand the interval limits or how to apply the y values correctly to the specific curve in front of them. It's like stacking heavy theoretical bricks without checking if the steel frame can actually support that much unorganized weight. It's a disaster waiting to happen. On the flip side, we have builder Sam. Sam loves to use shiny, descriptive words, writing out these long, beautifully worded paragraphs about the nature of the curve, but entirely missing the core numerical command words required to actually calculate the area. It's like putting up fancy decorative glass before you've even cemented the foundational columns. The reality? Neither of these approaches will pass the examiner's structural audit. Moving right along to Section 2, reading the system blueprint. Now, what's really interesting here is how we establish the official building regulations. These are the codes strictly enforced by Cambridge examiners. The entire theoretical architecture of the trapezium rule rests on these precise definitions and causal relationships. In fact, the examiners explicitly state in their reports that candidates who reference cross-topic connections achieve significantly higher marks. What does that mean for you? It means it is absolutely not enough to just memorize the basic trapezium formula. No way. You must rivet that formula to other areas of the syllabus. You have to build a highly adaptable mathematical network that can transfer seamlessly to completely unfamiliar contexts. You need to show exactly how the sum of the parallel sides relates to the strip width, no matter how weird or complex the exam question looks. So, the assessment objectives essentially enforce distinct cognitive domains. Let's break this down. The base level is knowledge and understanding. That's your foundational accuracy, stuff like knowing that your h value needs to be divided by 2. It's basic, but essential. But as we move up the high-rise to application and analysis, we require serious load-bearing scaffolding and tight logical reasoning. This means an evaluative structure will always outscore a purely descriptive one. Knowing how to calculate the area gives you breadth, sure, but analytical depth? That's knowing whether that calculated area is an overestimate or an underestimate based purely on the curve's concavity. That is how you drive your steel pilings all the way down to the absolute bedrock to secure top marks. And this brings us to a massive structural flaw I see out on the site all the time. Why do students find applying these concepts to unfamiliar contexts so incredibly hard? I mean, it's the #1 cause of instant collapse under the mark scheme criteria. Here's why. Students memorize a rigid, pre-built structure in their minds. But then, the exam throws a curveball. a complex, weirdly shaped curve, or asks for an evaluation of the approximation's percentage error. Because they memorized instead of understood, they fail to adapt their pre-built mathematical structures to this new terrain. The scaffolding snaps, and the whole calculation comes crashing down. Let's move over to the drafting board for Section 3, the ironwork peer debate. Let's listen in as our two builders from earlier debate how to construct a model response for a super high-tariff trapezium rule question. Alex naturally immediately wants to pour a massive solid block of terminology definitions right into the answer space, just a giant wall of text and numbers. But Sam steps in and correctly points out a major issue. If you pour a solid block of numbers without any context or explanation, there is absolutely no hollow space left for dynamic analytical evaluation. Think about it. Without room to evaluate assumptions, like mathematically proving whether the trapezium rule overestimates because the curve is convex or underestimates because it's concave, the structure has zero flexibility. It's too rigid. And without that flexibility, you're never going to hit those top-end scores. So the crucial takeaway here is what we call the method mark strategy. This is the ultimate site inspection criteria. Listen closely. Cambridge examiners do not just walk onto your construction site, glance at your final numerical answer, and hand you a grade. Absolutely not. They inspect the structural framing, they want to see every single weld, every support bracket, and the entire logical progression of your integration. Marks are explicitly awarded for the step-by-step process of your y-value substitution, not just the magical number that pops out of your calculator at the end. To construct this perfectly every single time, you need to use the deconstruct, solve, evaluate sequence. This is how you rivet your raw data directly to the core thesis column. Step 1. Deconstruct the problem. This means meticulously calculating your strip width, h, based on the limits given. Step 2. Solve. Break that complex formula down into systematic, logical steps. Ensure the first and last y values are isolated, while all those intermediate y values are properly doubled inside the brackets. Step 3. Evaluate. Step back from the mathematical framework you just built, check it for structural reasonableness against the graph, and mathematically justify why it holds weight. All right, Section 4, Mid-Build Inspection. Hold the concrete pouring. We are halting the construction clock for a live site inspection. We need to upgrade our cement before it dries. Before we secure this high-scoring paragraph framework, make sure your construction line is fully reinforced. Subscribe to Ace the Exams right now and turn on all notifications to receive our weekly structural grade upgrades. Whether you are building an IGCSE foundation or setting up an A-level skyscraper, this explainer is your primary grid. Okay, let's double-check our core integration process. Did you correctly calculate your interval width? Did you accurately substitute all y values into the equation? Have you carefully evaluated the concavity of the curve? These checks are absolutely crucial to ensure your foundation doesn't sink. The principal examiner reports have actually issued a severe warning across the site. They have isolated the top 3 structural failures that repeatedly show up in candidate mathematical responses year after year. These 3 command stress points will literally cause your marks to shatter if you aren't careful. First up, vagueness. This usually looks like prematurely rounding your values in the middle of the calculation, which totally throws off the final area. Don't do it. Keep the precision until the very end. Second, poor formatting. Students completely forget mathematical conventions. They place brackets incorrectly, which means their multiplication pilings are driven in at entirely the wrong angles. You multiply the wrong things together and the whole build fails. And third, generic answers. Simply writing down the formula without applying it to the specific coordinate limits given in the question is a guaranteed structural failure. Look at the stark difference here. A generic answer, just vomiting a memorized definition onto the page, is a massive structural failure. A reinforced framework, however, extracts precise, undeniable evidence from the given tables. It calculates the intervals methodically, and it explicitly links every single point, limitation, and assumption directly to the unique mathematical scenario provided in the exam. That is exactly how you engineer a heavy-duty load-bearing response block that an examiner can follow perfectly from top to bottom. To rivet these rules permanently into your mind before exam day, I want you to use the FACT memory hack. FACT. First, format your equation brackets correctly. Second, apply the correct H interval width terminology. Third, contextualize everything by calculating your y values precisely from the provided data table. And finally, think evaluatively about whether your final area is an over- or underestimation based on the curve. If you bolt those 4 principles together on every single calculation, your mathematical reasoning will be completely weatherproof. Finally, Section 5, it's time for the live viewer rebar stress test. All right, you have 60 seconds on the construction clock to conduct a safety audit. Look at this blueprint matrix. How do you interpret these relationships? Your job is to extract the single most high-yielding core metric from this data. Notice the nonlinear progression in those y values. Look at how the gaps increase. Notice the specific 0.5 intervals on the x-axis. A novice builder just takes these numbers and blindly punches them into a calculator, hoping for the best. But a master architect, they evaluate the relationship. They assess those increasing gaps and consider the curve's overall behavior before they substitute a single value into the trapezium formula. Top-scoring candidates survive this exact stress test by processing the data through 4 strict evaluative steps. Step 1. They identify the limitations in the given interval points. Step 2. They actively note the mathematical assumptions being made. Remember, we are assuming straight lines between points on what is actually a curve. Step 3. They consider alternative interpretations of that nonlinear relationship. And step 4. They evaluate exactly how those limitations affect the accuracy of the total calculated area. By doing this, they draw highly justified, structurally sound mathematical conclusions that the examiners absolutely cannot tear down. As we pack up our tools and roll up the blueprints for today, I want you to ask yourself this final question on exam day. Did you double-check your mathematical format, your interval spacing, and your evaluation of the curves specific to the context before you walked out of that exam hall? If you can confidently answer yes to that, then your mathematical skyscraper is structurally flawless. Keep practicing those past papers, keep reinforcing those calculation foundations, and we will see you on the next site build.